What's going on, guys? This is Stigward. Today we'll demonstrate how you can use a CVE description in order to identify the root cause of a vulnerability and write an exploit for it. Specifically, in this video, we'll pick a new critical CVE that just came out for a network-attached storage device. We'll reverse engineer the device's firmware to identify the root cause of the vulnerability, and then we will write an exploit for it. So with that, let's go ahead and get into the video. Okay, so the first thing you may be asking yourself is how do you actually pick a CVE to go after, to write an exploit for? And my answer is typically just to kind of go on the internet and look for different CVEs that have recently been released, things that you think might fit your skill set, targets you're interested in, etc. And so for this particular one, we were scrolling VulDB, which is a threat intel platform, and I was down here in the CVSS current top, which are the most severe rated vulnerabilities that have come out across this week. And we can see that this Zyxel company has released a number of vulnerabilities, all which result in remote code execution, all of which came out this week. And so I just jumped over to the security advisory, and I see that there are, like I said, a number. We saw each of these on the other platform. The one that immediately stood out to me is the CVE 2023-35138. And the reason for that is this one actually has more information than any of the other ones. So we see here that this one says like, hey, it's in the WSGI server, or this one says like pretty much nothing. But this one actually says a command injection vulnerability in the show Zyxel server contents function. So this gives us a point of reference to actually go ahead and look for the vulnerability. The other reason that this CVE is a good one to go after is because if we go down here, we can see that Zyxel actually provides us with full firmware downloads without having to do any hardware hacking or try to proxy the update traffic. Instead, we can see this is the patched firmware, and we still have access to the vulnerable firmware. And so we can go ahead and grab the vulnerable firmware right away and start digging into it. And then if we're still not able to locate the vulnerability with the information from the CVE description, we can grab the updated firmware and start to do a little bit of patch diffing and see what code was introduced that might have mitigated the previous vulnerability. So I've gone ahead and I have just grabbed the vulnerable firmware here and just renamed it so that it's easy to identify. We can see that it originally came in this .zip format, and so the first thing we're obviously going to want to do is just run unzip on it. This gives us three different files, the first being a PDF and the last being a PDF, so probably not super relevant to us, but we do have this .bin, which is most likely our firmware image. We can use a tool called Binwalk, which is written with the purposes of interacting with and extracting firmware images. And we can use the -e flag in order to run extract. And so if this finds unencrypted data in this image, it's going to automatically extract it and then allow us to navigate through it. So we'll run that on the .bin. And it should give us some output. Yep. And we can see that at these various offsets, it's starting to find different types of known data that it's identified. So we see it has a Linux kernel ARM boot executable image. We see some zip archives. And yeah, so it's run through, and Binwalk will always have the file name underscored, prefaced with an underscore, and then .extracted as the target unless you specify otherwise. So we'll just cd into that, and we can see that we have a new zip image, 2 files, and then a setup tools directory. We'll check out setup tools first. This is just a cli.exe, so most likely a tool for interacting with the device, not something we're going to be overly interested in. We're going to run Binwalk on these two as well and see if they give us anything of interest. So we'll start with the 6.8, file. And then once that one is done, we'll take a quick look at it. We can already see that this is a CPIO archive, so most likely our file system. So we'll cd into 6.8. And so we see CPIO root. This is going to be our file system. So once we cd into this, it should look very similar to a normal Linux file system. And we can see that we have all of the expected directories, and hopefully each of these are full. Sometimes you end up with weird weird instances where it's populated dynamically, but let's check bin. And yeah, so we can see all of these binaries. We can also see what type of CPU or what type of architecture the device uses. So we'll do file busybox. And okay, cool. So we can now see that this is 32-bit ARM. And that is what the device itself runs. So obviously, in that case, if we try and run it on our x86 machine, none of these binaries will actually execute. Cool. So we now have the file system. We're also going to take a look at what's in the other one. So let's run binwalk-e73, and we will extract this file as well. And this is a Linux ext file system. So a little bit weird. They have two different file systems here. Let's see if this one actually has anything in it. So if we cd into 7.3, and then we cd into ext. Yep, okay, so this also has some files in it. So let's check bin, and we can see that this has some additional binaries. And so at this point, we've recovered most of the file system. So we have the regular CPIO file system as well as this extended file system. What I'm going to do off camera is just go ahead and combine the two so that we have one kind of central file system. That might not be how the device actually works, but it'll give us an easy way to search through files and understand how the whole file system works together. Okay, so offline, what I've gone ahead and done is just combine the two file systems so that they're easily searchable and somewhat represent the device in a running state. We can jump back over to our vulnerability now and start to kind of create a methodology for how we're going to go about looking for the CVE. And so this gives us two pieces of information, really. The first is the function name. And so we can just do a quick recursive search across the file system to see if that turns up anything. The other here is that it is exploitable via an HTTP post request. This kind of indicates to us that it's most likely in the web server component of the Zyxel NAS device because it is hittable with a web request. And so if I'm starting to think about this critically from just this one sentence, I'm guessing that there is an API exposed from the Zyxel NAS device that we can hit with a post request. Something in the body of that post request eventually gets funneled down to this show Zyxel server contents. And in this function, there is a way to execute a system command with the attacker control data from the request. And so that's kind of the mindset we're going to go into it with, and we can confirm some of that stuff. We might have some wrong assumptions there, but that's where we're going to get started. And so the first thing I'm going to do is just copy this, and I'll do a quick grep for the name, and right off the bat we get 2 hits. This is nice, one, because if this was in a binary or something like that, we wouldn't actually get any hits, but right off the bat we can see 2 places where this function name is referenced. We can also see that this is in the local Apache directory, kind of confirming our suspicion that this is most likely in the web framework aspect of it. So why don't we go ahead and open up this one. And it would show, yep, here it is. Okay, so we can see here that we are assigning this get remote server content to this kind of CMD, whatever this is, backup planner main, and then show Zyxel server contents. So almost like a function pointer of sorts, maybe. We're not really sure. Let's scroll up and see what this is. So this is the command pool. So you can run these commands, I'm assuming, and somehow the command then gets forwarded to the corresponding function. We can see the actual command function. We get the incoming command, which I suppose is one of these, and then the function handler, and then if a write is needed. So what we can do based on this is we'll go back and find this, and we see that the associated command is get remote server content. And so let's go ahead and rip grep for get remote server content. And we can see one here is the same reference that we previously saw, but we can also see that it's being used as a URL in this backup add.js. So let's check this out as well. And we will do vim, and then we'll jump into that file and get remote. Cool. Okay, so here we can see that there is some sort of front-end request being crafted with some user-controlled data. Some user-controlled data. We have the server IP, we have the username, we have the password, and we have the share. And so this command is being sent to, we can assume based on the fact that we know the URL and we know that the URL is associated with our vulnerable function, we can kind of begin to piece together that this is the attacker controlled data in our post request. And obviously we're going to control the username and the password. And so maybe one of those parameters gets passed into a dangerous function and allows us to do our OS command injection. Now, it's pretty evident that this is part of the front end code, and we don't actually know where the handler is on the back end. And so that's going to take a little bit more looking to actually find the implementation of that vulnerable function. And so just to kind of confirm our suspicions, we saw that this was in a script called backup add or backup add. And so what I did was I just jumped on YouTube and I started looking through some of the Zyxel tutorials, and we see one called how to create a NAS backup job. And while they're walking through the step-by-step tutorial, we notice that one of the steps here asks for an IP address, a username, and a password. And if we think back to the front-end post request that we just identified, those are the three components that were a part of it. And so we can use this to first visualize kind of where we are on the device and what might be taking place, and also to understand that yes, we are in a front-end component. We do have the different parameters that are going to be sent to the back end, and now it's just a matter of identifying the web server and understanding how those parameters are actually processed. And so the next thing I'm going to want to do is I'm going to want to take a look at the initialization scripts. And so these are in etc and initd, and we can see them all here. The reason we want to take a look at these is because we know that the web server is going to have to be started up when the device turns on. And so most likely they're running the command to do that in the initialization scripts located here. I'm going to start with RCS2, and the reason for this is because when I was combining the two file systems, which I did off camera, the web server was in the ext file system, and the only initialization script in that ext file system was the RCS2 one as well. And so I'm guessing that they might play together. And so we can check here, and we're just going to go through it. I'm not going to try and like break down all of it. We're looking for one thing and one thing in particular. And so we see it doing some kernel setup stuff. We see it mounting some things. We see it creating an Apache. So here, right off the bat, we're creating a read-write dir for Apache. We're adding some account stuff. Then we see, okay, so it tries, this is all commented out, but it has WSGI server. So we can kind of understand that's probably the web server. And we see it's referencing ext Zyxel conf web framework. But again, this is commented out. Aha. So this is the one that we're interested in. The one that's not commented out says starting WSGI server, and then it goes to the main WSGI.sh, which is also in initd. So let's try and find that. Here we are. And so what this does is it is going to run it's either going to grab the PID or it's going to run Python user local Apache web framework and then main wsgi.pyc. And so this is originally this was a Python file. PyC is the bytecode format for Python. So you can actually essentially compile it down to PyC where it's not human readable. And we can see that they're running that to get the web server started. And so this is most likely the backend components of our web framework. And we can kind of go look there and maybe try and reverse engineer some of these PyC files. So if we actually change directory into the web framework that we saw in the init script, we can see that main_wsgi PyC file. We can also look at each of these subdirectories. So if we go into like controllers, we can see that this is full of PyC files as well. And so in order to reverse engineer these, we can use a tool called PyCDC. It allows us, as mentioned, to just go ahead and it takes Python bytecode and tries to recover the original Python file. So I've actually gone ahead and already grabbed that repository and used the build instructions to build the corresponding binary and moved it into this web framework directory, so you can see that here. And then I also went ahead and wrote a wrapper around that binary. So what this is going to do is, I'm actually going to change this. It's just going to grab the binary, and then it's going to walk through all of the subdirectories, and if it finds a .pyc file, it's going to run the pycdc binary against that file and output it to a new file with the .py extension. So it'll try and recover the original Python file and save it to a it will try to recover the original Python code and save it to a .py file for us to easily look through to try and locate that vulnerable function. So I went ahead and ran that decomp.py file that I showed in the previous cast, and it took a little bit of time, but it has finished now. And if we jump into one of the subdirectories like controllers, we can see that each PyC now has an associated .py. And if we were to cat out one of these like appzone _main.py, we see that it's done a decent job of trying to recover the original Python contents. So we'll jump back out to the main directory here, the web framework directory, and we will try and run another grep for the vulnerable function, show Zyxel. And right away, we get a hit on a function in the backup planner _main_model.py. And so let's go ahead and jump into that Python file. And so here we are, line 227 is our alleged vulnerable function from the CVE description. And if we take a look, the vulnerability, the command injection becomes very apparent relatively quickly. If we recall back to what we saw in the front end code, it was sending that IP parameter and the username parameter, the password, and the share. And so you can see here that each of these user supplied strings is being concatenated with this string command here, which is going to run the Zyxel binary and do some other stuff. That is automatically thrown into a process open command, which will just run it as a Linux command. And so if we can actually escape one of these strings and throw in a semicolon, we can, in theory, run our own Linux command here and have total command execution. So after figuring out the vulnerability, I actually went ahead and picked up a NAS device off of eBay for about $60 just to test the exploit here. So I have the add new backup job GUI aspect pulled open, which will generate our post request. And then I am going to capture that post request here in Burp Suite. And so if we go back to the web browser, we'll say 10.0.0.123, which is just a bogus IP address. And then we'll say fake pass, and we will click show target content. And we can see here that we've actually generated this URL or this post request to the show Zyxel server contents URL, which we know has our vulnerable function as the handler on the back end. So I'll go ahead and send this to the repeater, and then I will turn intercept off, and this will probably come back with failure, but that's okay. We have what we need here in the repeater. And so we're going to target the password parameter here. And I've actually already come up with a payload, which I will walk through now. And so here in the decoder, I have our command injection payload. And so what we're first going to do is we are going to insert just the password test. And then we are going to actually close the parenthesis in that format string. After that, we will add a colon to tell the command, hey, we're about to run a new bash command. And then we are going to run the curl command to our local IP on port 8000 and grab this rs.py file. rs.py is just a Python reverse shell that I've put together. This is because we already know the device has to have Python in order to run the web server. I did some digging and figured out that it was Python 2.7, and so I wrote a little Python 2.7 reverse shell here that just takes our IP and our listening port and establishes a connection. This is very similar to kind of one of the payload all things or one of those reverse shell cheat sheets. I've just put it all the way in a file, and I'm gonna download that file onto the device. And so we then output that to, with the -o, we output that to rs.py, so that will be saved on the local machine. And then we run the reverse shell payload, and then we just echo out in order to continue on with the original command. And so I'm encoding this as a URL just to make sure that there are no escape issues or special character issues in the actual post request itself. And so let's go ahead and set up our two things. We need to have a local server running. We need to have a local server running in this directory, and then we need to have a netcat listener on port 4444. And so we can go ahead and grab the password parameter. We will copy in our encoded payload here, and we will send that. And we can see that we did get a curl request to get the rs.py file. And if we check here, we now have a connection established. So if I run ID, I'll see that I have a root shell on the NAS device now. And we can confirm that we have the full directory listing. And at this point, we have full code execution on the device.